In this video, we're going to investigate some information about zero divisors inside the ring of integers modulo n. So we're going to let k be an element of Zn, and we're going to assume that k is a zero divisor inside Zn. Now, what that tells me is the following information. First of all, I know that k is inside the set 1, 2, 3, all the way up to n minus 1, and this is because k is inside Zn, and we know that k is not equal to 0 because no zero divisor is equal to 0, and k is a zero divisor. Now, the fact that k is a zero divisor also tells us this. There exists an a inside Zn such that, first of all, a is not equal to 0, and second of all, a times k is going to be equal to 0 inside Zn. And the question is whether or not these two facts that we have sitting in front of us let us make any conclusions about what's going on. So what I want to do is I want to actually start with this idea here. So what we're going to notice is this. Let's see, ak is equal to 0 in Zn is going to tell us that ak is congruent to 0 mod n, and that's going to tell us that n divides a times k, which is going to tell us that basically ak is at least as big as n. In fact, basically what we can be thinking of is that ak is equal to q times n, where q is some positive integer, and I know that it's a positive integer because everything at site is positive. Now, the question is what does this buy me? So what I want to look at is this stuff here. Does this let me conclude anything else? So what does this say about what's going on? Well, what I'm going to notice is this. We're going to make a note that since n divides ak, that tells me that ak is a multiple of n, and ak is also clearly a multiple of k. And so what does that say? Well, that says quite easily that ak is a common multiple of n and k. And what that means is that the least common multiple of n and k can't be any bigger than ak. And I want you to think about that for just a minute. So let's think about that for just a minute. We're going to recall that a has to be in the set 1, 2, 3, all the way up to n minus 1, since a is inside Zn, and I know that a is not the 0 inside Zn. So what this says is that a is clearly less than n, and it's clearly bigger than 0. And if I think about that, what that says is that ak is less than nk. And remember, ak is a multiple of both n and k. And so what this says is that the least common multiple of n and k is clearly not equal to n times k, and the only way that happens is if the GCD of n and k is not equal to 1. So what we've just gotten done doing is we just proved this particular important fact. If K is a zero divisor inside the ring Zn, then the GCD of n and k is not going to be 1. In other words, k will not be relatively prime to n. Well, the question then becomes, does this implication go both ways? In other words, one thing that mathematicians always do is once we prove an if-then statement, we start saying, well, is the converse of the statement true? So let's investigate the converse. And so what we want to do is we want to investigate that converse of what we just got done doing. So we want to investigate what happens when we assume that k is an element in Zn, k is not equal to the zero element, and the GCD of n and k is not equal to 1. And we're really wanting to know what the answer to this question is. And we're wanting to know whether or not k is a zero divisor inside our ring. So in order to investigate this question, what we're going to do is we're going to start with, what does all of these pieces of information actually tell us? Well, the first two things lets us know the following things. Since k is inside Zn and k is not equal to 0, that says k is in the set 1, 2, 3, 4, 5, 6, all the way up to n minus 1. And the fact that the GCD of n and k, I'm going to call that d, the fact that d is not equal to 1 says two things. First of all, it says there exists a Q1 such that n is equal to Q1 times d, and there exists a Q2 such that k is equal to Q2 times d. That's what the definition of a greatest common divisor is going to be. It's part of the definition. That's a definition of a common divisor. But the fact that d is not equal to 1 means in this particular thing, Q1 can't be equal to n, and in this step, Q2 can't be equal to k. So this particular fact here is going to imply two important things. Q1 cannot be equal to n, and Q2 cannot be equal to k. So what does this say? Well, this says that Q1 definitely belongs to the set 1, 2, all the way up to n minus 1. And this says that Q2 belongs to the set 1, 2, all the way up to k. But now I do want to remember that k is also known to be inside the set 1, 2, all the way up to n minus 1. So this set here is a subset of this set. And because of that, it turns out that if we look at this fact here and this fact here, these two things together say that Q2 is also actually inside the set 1, 2, all the way up to n minus 1. In other words, the upshot is that Q1 and Q2 both belong to Zn, and Q1 and Q2 are not equal to 0 inside Zn. So what else can we now say? Well, here's what I want to look at. I simply want to look at this. Let's look at multiplying. Let's look at multiplying Q1 times K. Now Q1 times K definitely belongs to Zn, since Q1 belongs to Zn and K belongs to Zn. So the question is what element is this equal to? So let's actually take the time to compute this. Q1 times K is nothing more than Q1 times Q2 times D, and that's because we know that K is equal to Q2 times D. Remember, that's because of this fact right up here. We're using this fact right there. Now, we're in a commutative ring, so I want to make that note. So recall, Zn is a commutative ring. So we can swap the order of both the parentheses and the elements. So this lets me say Q1 times K is equal to Q2 times Q1 times D, and I can put the parentheses in this particular place, but Q1 times D is equal to N, and that is congruent to 0 mod N. And so what this says is that Q1 times K is equal to 0 inside Zn. And that means we have proved the following implication. If K is inside Zn and K is not equal to 0, then, and the GCD of N and K is not equal to 1, then we know that K is a 0 divisor in the ring Zn. Now, if we put the two results together, we have the following interesting facts. From the first part of the video, we have if K is a non-zero element of Zn and K is a 0 divisor, then GCD of N and K is not equal to 1. The second thing that we've proven is that if K is a non-zero element of Zn and GCD of K and N is not 1, then K is a 0 divisor inside the ring Zn. Now we can put these two things together as an if and only if statement and say that what we actually have done is we have proved the following theorem. And this theorem says, let K be a non-zero element of Zn. Then we have K is a 0 divisor inside Zn if and only if the GCD of K and N is not equal to 1. And it turns out this is a very important theorem.